Imagine an endless, in all directions, completely empty, sterile room with not a single speck of dust in it and no light penetrating it at all. Now imagine a flashlight in there. That's great, but there's an inaccuracy here. The picture should actually look like this. If we were to look at a flashlight in the above-mentioned room from the other side, we would not see the flashlight itself, nor the beam it emits. Paradoxically, light is invisible, and invisibility is one of its most understood properties. We only see it when it hits our eyes. We can't see light that just passes by without reflecting off of anything. If there had been a second light source there, we might have seen the flashlight, but again, not its light. Rays of even the most intense light we can get pass through each other as if there is nothing at all in their path. Remember that. Now imagine that the flashlight is shining directly into our eyes, and we are gradually flying backwards away from it. The reflector will seem to us smaller and smaller, and then it will turn into a point. Then, as we move further away, the point will become more and more dim. When the distance between your eyes and the flashlight reaches 10,000 kilometers, the dull dot will disappear altogether, but that's if we're talking about the human eye. The frog's eye is several times more sensitive than the human eye, which is just enough for the experiment to produce a significantly different result. If the observer is a frog and it moves away from the electric flashlight, the moment when it completely loses sight of it will never come. Instead, the frog will start to observe an entertaining picture. It will see that the flashlight has started flashing at non-equal intervals. These intervals will increase as they are removed. At a distance of 100 million kilometers, a frog will on average see only one flash of light a day, but that flash will be as bright as any other throughout infinity. This flicker proves that there is a limit to the uniform stretching of light. Each flash the frog sees is caused by a photon hitting the retina of its eye. Moving away from the flashlight, the photons themselves do not become weaker, but the light beam weakens due to the fact that the free space between the photons grows, then the frog sees nothing. This is not because the light entering her eyes is too weak, but because no light enters her eyes. This property of appearing only as pieces of discrete sizes is called quantization. A single piece of light, a photon, is called a quantum. Quantum theory derives its name from this property that it attributes to all measurable physical quantities. Yes, in physics there are no measurable continuous quantities. Everything that surrounds us and seems continuous, in fact, is not. This video is based on British theoretical physicist David Deutsch's book, The Structure of Reality. It's his opus magnum. Here Deutsch expresses his momentarily ultimatum view of what the universe is. He expresses it rather confusingly, probably because he's more of a scholar than a writer. Therefore, I have quoted something from the book, rewritten something, edited something, given other examples somewhere, added a lot from alternative sources, all for the sake of completeness of the picture and greater accessibility. Deutsch's idea is pretty interesting, though I certainly wouldn't say I agree entirely with what's written here, and it is unclear whether it is because the author does not always clearly and concisely express his thoughts, or simply because I am not smart enough to understand him. David Deutsch, you know, the science rebel. He sure took a jab at quite a few people in academia with this book. But the video probably won't be nearly as much about that as it will be about why we almost certainly live in a multiverse. Multiverse, parallel realities, alternate worlds, absolutely commonplace expressions in our everyday vocabulary. Almost everyone applies these phrases in life, saying, for example, about unlikely events, like here in one of the parallel universes, I am a billionaire. But let's be honest, no one takes the idea of multiverse seriously, and most are not even aware of what this idea means within the framework of physics, actually. And it means a lot of things. Many universes are described in their own way in different physical concepts, and many of these concepts have the right to exist. We will speak about the many worlds interpretation of quantum mechanics, which being both direct and almost the simplest consequence, shows us a whole new view on the world. For a second, so new that when scientists began to discover little by little the laws of quantum mechanics, they naturally tried to explain what they were seeing in the first place. In the end, they were so desperate that nowadays it is considered quite a bad tone among specialists in quantum theory to talk about something other than equations. An attempt to explain what these equations are about is immediately written down as idle chatter. David Deutsch, in turn, despises such an instrumental approach to physical theory. From his point of view, and in this I absolutely agree with him, the desire is not only to predict and use, but to understand. It's perfectly normal. You know what's weird? Quantum mechanics is the most tested and most successful theory in the history of science. The main proof of this is the fact that you are watching this video at all, since it was quantum mechanics that became the theoretical basis for semiconductor electronics. And for all that, I'll say it again, we don't have an understanding of what it is. If, for example, Einstein's general theory of relativity tells us about the curvature of the space-time continuum, then what quantum mechanics says no one knows. All we have are interpretations, and all we can do is argue which one is better. Okay, what's so mysterious going on down there at the quantum level? I'm sure you've heard of the two-target experiment many times. If not, I'll briefly tell you about it now. Feynman was fond of saying that all of quantum mechanics can be derived from just one careful thought about the consequences of this one experiment. And so, take the foil in which we make two small slits at a distance of 1/5 of a millimeter from each other. Behind the foil, we'll set up a screen, take a regular laser, and shine it on the slits in the foil. If light propagated in a straight line, then in this experiment we would see two bright stripes with sharp boundaries located at a distance of 1/5 of a millimeter from each other. But what we actually get is a lot of bright and dark stripes without sharp boundaries. Pretty unusual. Well, what kind of shadow do we get if we cut two more slits in the remaining space between the two slits? So we will have 4 slits spaced 1/10 of a millimeter apart. You'd expect the picture to look pretty much the same, but in reality something completely different is happening. We see that the shadows of the 4 slits are not a combination of 2 slightly shifted shadows from 2 slits, but have a different structure. There are areas in this picture such as point X. These areas were illuminated when there were 2 slits in the partition, but suddenly ceased to be illuminated when 2 more slits were cut in the partition to let light through. Thus the appearance of 2 additional light sources dims the point X, and their removal again illuminates it. It's a bunch of bullshit. Nevertheless, the basic idea cannot be avoided. Through the second pair of slits, there is something preventing light from the first pair of slits from entering the X zone. But what? What is causing the interference is obviously in the light beam itself, and whatever it is behaves exactly like the light itself. It is always present in the beam of light, but absent outside it. It is reflected, transmitted, or blocked by that which reflects, transmits, or blocks light. The only answer is that it is light, that is, photons from one slit are interfered by photons from other slits. Well, how can they interfere if photons don't interact with each other? Remember, I talked about this back at the beginning of the video. Okay, well, what if they do interact? Performing the same experiment, but firing only 1 photon at a time from the laser, just in case. We will get exactly the same thing. Even in the experiment with single photons, we will not see a single case of their hitting the point X if all 4 slots are open. But just close the 2 slits and the flashes at X will resume. Maybe the photon still splits into fragments which, after passing through the slits, change their trajectory and reunite again. But no, by installing a detector at each slot, we will never see even 2 detectors going off at the same time. What is it? When we fire 1 photon at a time in our experiment, something gets through the other slits and interferes with the original photon. It's something intangible and invisible. We can't pick it up with instruments. Let's take a critical look at this issue. We found that when a single photon passes through this machine, it goes through 1 slit, then something acts on it, causing it to deviate from its trajectory. This impact depends on what other gaps are open. That is, objects affecting a photon pass through other slits and behave the same way as photons, but they are invisible. We can assume that these are some kind of shadow photons that can only be detected indirectly through their effects on real photons. Thus, each real photon is accompanied by an escort of shadow photons, and when a photon passes through one of the 4 slits, some shadow photons pass through the remaining slits. There are clearly many more shadow photons than real photons. Deutsch and colleagues concluded that there is no upper limit of the number of shadow photons, but the very minimum is 1 trillion shadow photons per 1 real photon minimum. Now that's a careful thought right there. What must happen at the microscopic level when shadow photons meet a light impenetrable barrier? No doubt they're stopping. We know this because interference stops when a light-tight baffle appears in the path of shadow photons. But why? What's stopping them? They certainly can't be absorbed by real septum atoms. Because given the estimated number of shadow photons, the baffle would just vaporize, literally. Anyway, we'd fix it easily in a bunch of different ways. Shadow photons do not interact with real atoms, and yet the baffle affects both real and shadow photons equally. It stops them, but shadow and real photons in turn affect the partition differently. In fact, as far as we know, shadow photons have no effect on it at all. And yet they stop, hence. You know what that means? In the place where the real partition exists, there is also a shadow partition. It's just an inescapable conclusion. Without much effort, we realize that this shadow partition consists of shadow atoms, in which, as we already know, should be present as twins of real atoms of the partition. Every real atom has many doppelgangers. In fact, the total density of shadow atoms, even in a weak fog, is more than enough to stop a tank. What to speak of a single photon if these atoms could affect it? You can stop me and say that's too far-reaching a conclusion. It's a microcosm. How can you talk about whole parallel universes basing your conclusions on photon interference alone? Quanta of light. They don't even have mass. But we have already now obtained an interference pattern on fullerene molecules. Fullerene is a form of pure carbon. You know what I mean? It's practically a classic object. In other words, particles are grouped into parallel universes. They are parallel in the sense that within each universe, particles interact with each other just as they do in the real universe. But the influence exerted by each universe on the others is very weak, and it manifests itself through the phenomenon of interference. Thus, we have deduced a chain of inferences that begins with strange shadow pictures and ends with parallel universes. At each stage, we discover that the behavior of the objects we observe can be explained only by the presence of invisible objects and their certain properties. The basic idea is that single-particle interference definitely rules out the possibility of the existence of only the real universe that surrounds us. Nevertheless, the theory of the existence of the multiverse has not been very popular among physicists for a long time. Why? Because her conclusions are obviously too grandiose to accept. Some practicing physicists ask, why can't we just say that photons behave as if they collide with invisible objects? Why should we go further and accept the theory that these very invisible objects exist? The real photon is tangible. The shadow photon is just a way of possible, but not realized behavior of the real photon. Quantum theory is about the interaction of the real with the possible. Why can't we just leave it like that? Because, says Deutsch, the possible cannot interact with the real. Non-existing objects cannot change the trajectory of existing objects. If a photon deviates from its trajectory, it must be affected by something. It cannot be that the actual and eventual appearance of the detection of a real photon is caused by an imaginary event. What the photon could have done, but didn't. As I said, interference is not only characteristic of photons. Quantum theory predicts, and experiments confirm, that interference occurs with any particle. Thus, every real electron must be accompanied by a mass of shadow electrons, every real neutron must be accompanied by a mass of shadow neutrons, and so on. So reality is much more than it appears, and much of it is invisible. We could call the set of shadow particles a parallel universe, for shadow particles are influenced by real particles only through interference phenomena. But we can do even better. After all, shadow particles are separated from each other, just as the universe of real particles is separated from them. In other words, they form not one homogeneous parallel universe, but a much larger one than the real one, and a huge number of parallel universes, each of which is similar to the real one in composition and obeys the same laws of physics, but differs from the others by the arrangement of particles. Let's return to the two-slit experiment. What will happen if we put dictors near each slit and try to catch a split photon when it passes through both slits? In this case, the quantum will always be caught exiting only one slit, but never both, which is natural if to take into account that quantum is not divisible by definition. And yes, the interference pattern on the screen suddenly disappears, replaced by a normal two-band distribution. You might say, well, yeah, no surprise, since at the subatomic level, you can't measure anything without interaction. When trying to find out which slit a photon flies through, the detector simply affects it and changes its behavior. All right, so be it. However, if to install only one detector near only one of slits, the quantum, even not being caught flying through another slit, will not show interference. That is, the quantum, just think about it, somehow found out that it is measured at another slit and refused to interfere. That is, the mere existence of the possibility to obtain information about the slit through which the photon has flown deprives us of the possibility to see the interference. It's just mystical, and there's a whole new religion growing out of it. The materiality of the observer's thoughts affects the universe by the mere fact of its observation. All these prejudices have been fostered by, what do you think? The classical interpretation of the founding fathers of quantum mechanics. The classical interpretation, or also called the Copenhagen interpretation. This is the most common view among those scientists who choose to accept any explanation for themselves at all. Its adherents separate peacefully quantum observables and classical measurement devices, which in itself is pretty weird. Thus our photon, a quantum object before measurement flying through the slits, behaves as some probability wave. That is, it is in a superposition of quantum states. But as soon as this probability wave interacts with a classical system with a screen or with a detector, then it immediately collapses, becoming a particle at some particular place. That is, until the photon is observed, it is a wave, but at the moment of measurement, it becomes a particle. Within the Copenhagen interpretation, this is called the collapse of the wave function. Einstein exclaimed, "I'd like to believe the moon is still there, even if we're not looking at it." You have no idea how many times and in how many variations the two-slit experiment has been done in an attempt to bring back common sense. All for nothing. And it all sounds wild to say the least. Wild within the framework of the Copenhagen interpretation. And despite the fact that it has gathered the largest number of supporters, David Deutsch believes that in fact, among scientists, no one has believed in it for a long time. In 1957, American physicist Hugh Everett was the first to clearly realize that quantum theory describes many universes. No one particularly listened to him in those years, but now many experts agree that it is the many worlds interpretation that closes almost all questions about the strangeness of the subatomic world. What does Hugh Everett's much worldly interpretation really say? She says that actually with observation, the interference doesn't go anywhere. Yes, and in general, that the phase of observation destroys interference is quite misleading for 3 reasons. First of all, it assumes some psychokinetic influence of a conscious observer on basic physical phenomena, though such influence, alas, does not exist. In the second, interference does not collapse, and it is simply much harder to see because it requires controlling the exact behavior of many more particles. And thirdly, not only observation, but any impact of a photon on its environment depending on the chosen trajectory does the same. And most importantly, am I really a billionaire in some parallel universe? First of all, what do you mean me? It's not me anymore. A crude analogy can be made to identical twins. Genetically, they are identical. We were once one zygote, but now can we say that your twin is you, especially since the differences between you will grow over time? And secondly, no one can tell you exactly how many universes there are. If there are not an infinite number of universes, then there are so unlikely events that there are none in the multiverse. If there are an infinite number of universes, then everything that can happen happens in the multiverse. Anything that does not contradict the laws of physics, including a universe where the sun just exploded because all of its atoms happened to rush toward the center. Of course, this event is only a negligibly thin branch of probability in the multiverse. But such a branch is there. Strictly speaking, in this case, there is an infinite number of universes in which the sun exploded, but this infinity is incomparably thinner than the infinity of universes in which the sun feels normal. Yes, even though there are an infinite number of universes, they have different densities. If it's not clear, here's a simple example. The infinity of natural numbers is greater than the infinity of even numbers. The many worlds interpretation, unlike the Copenhagen interpretation, says the whole world is quantum, which is much more consistent than the Copenhagen quantum classical world. In the many worlds interpretation, there is no mystical observer that collapses the wave function. Instead, there is a process of constant splitting called decoherence. In the two-slit experiment, photons fly through the slits in all possible ways simultaneously, and by measuring the photon, we become entangled with it and ourselves split into all versions of ourselves, measuring the photon in all possible states, thereby spreading out the branches of probability in the multiverse. You may ask, what is the measurement even? How does the universe realize that a photon has been measured and the pair is separating? This is where the law of entropy comes into play. Entropy is a measure of irreversible energy dissipation, and measurements are any interaction that is irreversible. And the observer doesn't have to be rational at all to do that. That is, the moon really exists while no one is looking at it, because the moon is an immense macrosystem in which irreversible interactions are continuously occurring. Measuring a quantum system which is in superposition, the observer becomes entangled with it and splits itself into all possible variants of itself, thus appearing for another third-party observer in superposition. Then the second observer observes the first and also gets entangled with it, and also splits into all possible variants of itself, and so on until the whole universe is involved. Any solid is made up of a collection of atoms, which in turn are made up of electrically charged particles. But because of classical chaos, no aggregate of charged particles could remain stable under classical laws of motion. The positively and negatively charged particles would simply snap out of their seats and collide with each other. Only strong quantum interference between different trajectories of charged particles in parallel universes prevents such catastrophes and makes the existence of solid matter possible. But then again, if we can already make even molecules interfere, why can't we do the same with the moon? Because of the complexity. A few molecules are nothing compared to a huge cosmic body, and superposition requires absolute isolation of the quantum system from the outside world. You have no idea what insulation is like. For the moon to be in a state of superposition, it is necessary to remove all photons that can be reflected from its surface. Because if even a single photon does it, it will be an irreversible interaction, and the superposition will disappear. Similarly, we would have to cool our satellite to absolute 0 Kelvin, because if the temperature were higher, the moon would again emit photons into the environment. Absorption of these photons by anything would be an irreversible act of interaction. But even if the above conditions are met, it still won't work. Because just one atom flying near the moon and changing its trajectory under the influence of its tidal forces will irreversibly change its trajectory. Isolation of the quantum system from the outside world, this is the main problem in building quantum computers. Although the absolute majority of experts still agree that the creation of full-fledged quantum computers is only a matter of time. Quantum computers will be able to accomplish in minutes or even seconds the tasks that would have taken conventional computers hundreds of billions of years. How? Through parallel universes. While a conventional computer performs operations sequentially, a quantum computer performs all tasks in parallel using the superposition phenomenon. For example, by using a quantum algorithm called the Shor algorithm. To decompose a 250-digit number into multipliers, the number of interfering universes would be on the order of 10 to the 500th power. It's a staggeringly huge number. David Deutsch proposes to try to explain the operation of Shor's algorithm without involving parallel universes. I don't mean predicting what the results of the Shor algorithm will be, since solving a few consistent equations is enough to do that. I'm asking you to explain. When the Shor algorithm decomposes a number into multipliers using about 10 to 500th times more computational resources than what you can see in person, where does that number break down into multipliers? There are only about 10 to the 80th degree atoms in the entire visible universe. The number is negligible compared to 10 to the 500th degree. Thus, and if the visible universe were the space of physical reality would not even remotely contain resources sufficient to decompose such a large number into multipliers. Yes, quantum computers exist today, but their power leaves much to be desired. To make them more productive, it is necessary to increase their complexity, and the more complex they are, the more acute is the problem of isolation, since the rate of entanglement of a quantum system with the surrounding world is higher the more complex it is. And so not the moon, not Schrödinger's cat, not even a speck of dust suspended in the air can be in superposition on any measurable time scale. Time? Do you even know what time is? We all think we know, but not until we're asked to explain. Quantum theory, and in particular the many worlds interpretation of it, among other things, invents a new concept of time, because what we have now in terms of Deutsch is contradictory, internally incoherent nonsense. For millennia, we have thought of time as a flowing river, that the present moment that we call now is not stationary, but is constantly moving toward the future. Or that moments from the future are whizzing past the present to become moments of the past. If one sits down and calmly ponders these provisions, there may seem to be something profoundly paradoxical about them, as if we have a certain true only now, and all the rest is either an undiscovered future or an already accomplished past. And it is only we humans who are attentive to the reality around us, we are fellow travelers of this true now. Of course, from the point of view of a particular observer, a particular moment does stand out, and it is only this particular moment that the observer can name now, just as the particular position of the observer in space is highlighted as here. However, even though space is three-dimensional and time is one-dimensional, objectively no single moment is more privileged to be called now than all others, just as no place in the universe has a greater privilege to be called here than all others. Deutsch writes, people understand that here exists only subjectively, but they don't realize that now is also a subjective category. Objective doesn't exist in nature right now, just like there's no objective here. You know, there's no real, it's an illusion. Space-time is sometimes called the block universe because it represents all of physical reality, past, present, and future once and for all, frozen in one four-dimensional block. In relation to time-space, nothing moves. What we call moments are certain layers, or as Deutsch says, snapshots of space-time. And when the contents of these layers differ from each other, we call it a change or movement in space. Adopting this model, we will notice that our consciousness exists in all moments when we are awake. The various snapshots of the observer are not in some mysterious present one at a time, nor do they become conscious of their present one at a time. Each snapshot of the observer perceives its moment as now. They are all awareness, and subjectively they are all in the present. Objectively, however, the present does not exist. According to such a concept, we do not feel that time is flowing or passing. We, thanks to entropy, feel the difference between our present sensations and our present memories of past sensations. I'd call it kitchen domestic philosophy if it weren't for one experiment that John Wheeler came up with. At that time, it was only a mental experiment, but in 1999, physicists were able to put it into practice. And that's what it's all about. We take a standard setup for launching single photons, but behind the baffle we install a beta-barium crystal, due to which one photon is converted into two entangled photons of lower frequency. And because these photons are entangled, we can make measurements on one photon without interacting with the other. A little to the side, we will position the lens so that it always combines photons from the upper and lower slits in detector number 1. Thus, this lens erases the information about which slit the photon passed through. We now perform some measurements with another pair of entangled photons from both slits. Each will hit a different beam splitter, which is placed so that the photon has a 50% chance of reflecting downward and a 50% chance of flying through. Those photons that will be reflected are combined so that it is impossible to know through which slit the photon has passed. In other words, if detector number 4 registers a photon, we don't know which slit it traveled through. It's actually called a quantum eraser. Note that detector number 2 can only detect photons from the upper slit, and detector number 3 can only detect photons from the lower slit. It may sound rambling, but bear with me. The results will stun you because here's what's going on. When detector 2 registers a photon, detector 1, which registers its entangled double, shows that this particle, not a wave. Because we see two fringes, not an interference pattern, the same thing happens with detector 3. No surprise, because detectors 2 and 3 register photons from specific slits. However, when detector 4 detects a photon, we already see an interference pattern that appears on both detector 4 and detector 1. Due to the fact that I know through which slit the photon is passed, the interference does not disappear. Nothing new so far, right? You haven't noticed anything? There is one detail that makes your skin run cold, and that detail is that the way to detector 1 is much shorter than the way to detectors 2, 3, and 4. Thus, a photon is always detected by detector 1 long before its entangled double is detected by any other detectors. The pulpiest part is that an interference or two-band pattern forms on detector 1 before the entangled photons even reach the splitter light. That is, the photon knows in advance whether its entangled double will reflect from the holy divider or fly through. I'm going to give you a few seconds to realize that. This result was repeated in all subsequent experiments, time after time, over and over again. It would seem that the measurement of a photon in the future affects its state in the past. There's a violation of causation. Aren't you sick of the fact that according to the physics we have hypothetically violated causality in general a lot of places? Binary black holes, wormholes, the first moments of the Big Bang, and so on. We say, oh, paradox, that's bad. Everyone gets upset at once, tries to solve this paradox somehow, inventing all sorts of complicated principles of self-consistency. But first of all, who said causality even exists? And secondly, the many worlds interpretation at ease resolves all these issues. Since nothing in the block universe is changeable, one part of space-time can change another, no more than one part of a fixed three-dimensional object can change another part of it. But let's make it even simpler, shall we? If we observe where one element of a fully assembled mosaic is located and know the shapes of all the elements and that they are correctly assembled, we can predict where all the remaining elements are, but that doesn't mean that the element whose location we observe is the reason that all the other elements are where they are. Is there such a causal relationship? It depends on how the whole mosaic was assembled. If the element we observe was put there first, then it is indeed one of the reasons other elements are where they are. If another element was put down first, the position of the element we observed was a consequence of that, not a cause. But if a mosaic were created by a single stroke of a blade having the shape of that mosaic, then none of the positions of the elements would be neither the cause nor the effect of the other positions. They would not have been assembled in any order, but would have been created at one time in such a position that the rules of mosaic would already have been observed, which would make these provisions mutually predictable, yet none of them would cause the others. So the determinism of physical laws about events in space-time is like the predictability of a correctly assembled mosaic. But David Deutsch goes even further and says that physical reality is not just a block universe consisting of space-time like a recorded movie with one unchanging plot. No, it is a much larger and more diverse entity of the multiverse in which the stories are infinite. They run parallel to each other, overlapping, intersecting, and branching. However, if you envision all universes on a single timeline, then forget it. Because, mind you, in the multiverse, other times are also just special representatives of other universes. This understanding first emerged from early studies of quantum gravity in the 1960s, in particular from the work of Bryce DeWitt, but as far as is known, the general case was not formulated until 1983 by Don Page and William Wooters. The snapshots we call times in our universe are different from other universes only from our perspective. And it is only in this that the laws of physics particularly connect them to our snapshot. Traditionally, we have placed other times and other universes in completely different conceptual categories. Now we see that differences are not necessary. You know, time is special cases of other universes, and this explanation solves all paradoxes over time. Rather than imagining how the multi-universe unfolds in time, Deutsch thinks it would be consistent to do the opposite. We have to imagine how time unfolds in the multiverse. Other times are just special cases of other universes. Some of these other universes, writes Deutsch so strongly, resemble our own. Ours now that we interpret them as parts of the history of our universe rather than as separate universes. For us, they are not somewhere in space, but on our timeline. However, in reality, our timeline, every moment of time, is a different universe. And from David Deutsch's point of view, that's exactly what the mechanism of time is. If so, it is no wonder why time is so ephemeral and elusive. Who knows how many universes you've changed since you started watching this video? So if we suddenly ever discover traveling back in time, it will not cause any controversy. Killing your grandfather would not create paradoxes, because traveling back in time would be traveling to other universes, very different universes. In this case, in a universe in which a person with your genetic code was never born. In the delayed choice experiment, the future does not affect the past. Photons show an interference or two-band pattern simply because all the choices of the future are already there, as are all the choices of the past. All information from the beginning to the end of time simply already exists in the multi-universe. In this sense, the many worlds interpretation is absolutely deterministic. From the beginning to the end of the universe, everything that could happen has already happened. All scenario variants are already written and exist on different probability branches, or if you like, multiverse sections. If numerous completely identical copies of me exist in other universes in addition to other versions of me, which one am I? To accept that this question has a physical meaning is to accept that outside the multiverse there is some reference frame relative to which an answer can be given. I'm that third from the left, but what left could it be, and what does third mean? Such terminology only makes sense if you imagine that the snapshots of me are lined up in various positions in some external space. But then on multiverse, there is no external space, just as there is no external time. All existing space and time exists in the multiverse. The multiverse, on the other hand, simply exists, and physically, it is all that exists. So, if you've ever wondered what happened before the Big Bang, or what would happen after the Big Bang compression, if any, now you may lose that interest. Multiverse neither begins nor ceases to exist. These terms imply a flow of time that does not exist. Just the representation of the flow of time makes us curious about what was before or what will be after all reality. We exist in a multitude of variants in universes called moments. Each variant of us is not directly aware of the others, but has evidence of their existence because the laws of physics link the contents of the various universes. No illustration or even approximation I can give of what the multiverse looks like. Any visual presentation is just a neutered semblance. But sometimes I think that sometimes for a split second I can almost visualize him. But you can shake off the above and wail. What are you talking about? Does Deutsch really suggest creating an infinite number of new universes at every moment just to explain the fucking shadow pattern in the slit experiment? I'll say it again. Universes don't come into existence, they already are. And yes, paradoxically, The many worlds interpretation is not multiplying entities. It doesn't require anything other than a mate. Many believe that the many worlds interpretation is not even an interpretation, but the most direct reading of the equations of quantum theory. Trying to explain quantum mechanics in any other way, we come to the conclusion that things only get worse and more confusing. So from David Deutsch's point of view, the many worlds interpretation is so far the best explanation of the structure of reality that we have, as we see it answers many questions, including philosophical ones. It can explain to us why what we call free will is possible, and at the same time that freedom has nothing to do with chance and that there is no contradiction. The many worlds interpretation even closes an explanatory gap in Darwin's theory of evolution by answering the claim of how such complex adaptations could have evolved in such a short period of time. If there are an infinite number of universes, then in a multi-universe there are all the humans that could have come into existence. The eminent physicist Bryce DeWitt, in Historical Correspondence, raised a number of detailed technical objections to Everett's many worlds theory, each of which Everett refuted. DeWitt concluded his evidence on an informal note, pointing out that he just can't feel like he's splitting into numerous different copies whenever he makes a decision. Everett's reply sounded like an echo of the argument between Galileo and the Inquisition. He asked, "Do you feel the Earth turning?" DeWitt admitted defeat.